In this presentation, I continue on to Poisson as a specific case of the chi-square test, looking specifically at spatial data such as in mapping. Of course, there is more to learn about logistic regression, but there are other approaches, and one of these you may read about is Poisson regression, which tests spatial clusters. Obviously, spatial clustering is important for geographic mapping, identifying the source of an outbreak, identifying environmental risk factors, and/or risks related to a neighborhood or zip code. Mapping clustering of risk can help to identify environmental factors associated with malaria, identify health risks related to a neighborhood or zip code, and test clustering in the occurrence or the probability of illness in a district, state, or country. In order to illustrate the idea behind Poisson regression, I'll use the example from the book. In the example, the authors gave a square with 200 points generated at random over 100 squares. Is there clustering? The Poisson regression asks this question by posing the null hypothesis. Is the distribution at random? The p-value will tell us how likely it is that the clusters are distributed at random. If that chance is very small, we reject the null and conclude with 95% confidence that the result is not random chance. So how does it work? Here I'm laying out the example as given in the book to show where they get some of their numbers from. In Table 5.1, they use the example of 200 hits, marks, or counts, and 100 squares. The average hits per square would be 2. Probability estimates are determined based on the mean value of hits or counts and the number of subdivisions, in this case with the mean being 2. So here is the formula as written in the book. Although it looks complicated, it's really quite simple. The lambda symbol represents average hits, which is simply 2. This is the instances of occurrence over the number of spatial blocks, squares in this case. If the hits were random, each blocks would have, on average, 2. So, filling in the numbers for the formula all the way down, these are the probabilities of a square having 0, 1, 2, all the way through 7 hits. It makes sense that the greatest probability is between 1 and 2 hits, and the smallest probability is 6 or 7 hits. The formula is the mean taken to the power of the number of hits divided by the number of hits factorial. 1 factorial is simply 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1, etc. Here we see the table from the book relating to the number of squares that have 0, 1, 2, 3, all the way up to 7 hits. The first row reflects the number of squares that had given the number of counts ranging from the 15 squares with 0 hits to the 1 square with 7 hits. The second row shows the proportion. 15 out of 100 squares is a proportion of 0.15. So here you see the second row is directly comparable to the probability. They used a total of 100 to make it easy to follow the math, so you could see that 15 squares is a proportion of 0.15. The probability of no hits in this table, based on the formula, is 0.135. This is the value that was shown in the previous slide, which when applied to 100 squares would be an expected count of 13.5. The third row is the probability calculated in the earlier slide, making use of the formula of the probability given in the book, the 0.135. And from that probability, it's easy to get the expected 13.5 counts. Given a probability of 0.135, we would expect 13.5 squares to have 0 hits. Probability can be seen as a proportion by multiplying it by the total you get, the expected number of counts. Note that the number is not realistic. There are no half squares in reality, but the number you get is based on the mathematical formula. Ultimately, the Poisson is another type of chi-square, comparing the observed and expected. We expect that if the hits are at random, the sample variance will be the same as the mean. Finally, in reading the literature, or if you ever use Poisson regression, you can interpret the p-value of the Poisson regression as testing the probability of no spatial pattern. Specifically, the chi-square test is testing whether the variance seen, in this case a calculation based on the formula in the book, came to the result of 2.081 as reported in the book. This is not different from what is expected, the mean of 2.00. The null hypothesis is no difference, and the probability or the p-value of 0.372, which is given in the book, indicates no difference is a likely or probable explanation. So just note the book gives the formulas but not all of the intervening steps. So the calculated variance and the p-value are simply given as facts, and the expected variance is based on the mean.